Every clock you've ever seen, every heartbeat, every sunrise, all of it depends on one quiet assumption, that time keeps going. But does it? Physicists have spent decades tracing the universe forward, past the death of stars, past the evaporation of black holes, into an unimaginably distant future where nothing seems to happen at all. And yet, some of the very people who mapped out this cosmic ending, including Nobel laureate Roger Penrose, believe that the end of time might not be an ending at all. In this documentary, we follow the universe through its final chapters, the last stars flickering out, the slow evaporation of black holes into nothing, and the strange thermodynamic stillness known as heat death. We examine competing theories, the Big Crunch, the Big Rip, vacuum decay, and we explore Penrose's own radical proposal, Conformal Cyclic Cosmology, which suggests that the end of time might secretly be a new beginning. This is not science fiction. This is where current physics run to its logical extreme actually leads. Some of it is settled science. Some of it is educated speculation. We'll be honest about which is which every step of the way. If you've ever wondered whether time has a final page and what might be written on it, this is the video for you. SEO keywords: end of time, heat death of the universe, what happens after the universe dies, Roger Penrose Conformal Cyclic Cosmology, Entropy and Time, Arrow of Time Explained, Black Hole Evaporation, Hawking Radiation, Big Crunch versus Big Rip, Vacuum Decay, False Vacuum, Fate of the Universe, Thermodynamics Documentary, Cosmology Documentary, Physics of Time, Second Law of Thermodynamics, Universe's Final State, Eternal Inflation, Cyclic Universe Theory, Does Time End? Future of the Universe, Script. Somewhere right now a clock is ticking. You can hear your own heartbeat. You can watch a candle flame lean and flicker. All of it, every motion, every change, every heartbeat in every chest on Earth is powered by the same invisible current, the flow of time. We treat it like the most reliable thing in existence. The sun will rise, the seasons will turn. Time will keep moving the way it always has. But here's the question almost nobody asks, because it feels almost meaningless to ask it. Does time actually end? Not does the world end, not do we die, but does time itself, the dimension that lets anything happen at all, eventually run out of things to do and simply stop? It sounds like a question for philosophers late at night after too much coffee, but it isn't. It's a question physicists can actually calculate an answer to. And when you follow the mathematics far enough into the future, past the death of the sun, past the last flicker of the last star, past even the slow death of black holes themselves, you arrive somewhere almost impossible to picture. A universe so empty, so cold, so quiet, that some scientists have wondered whether time, in any meaningful sense, still exists there at all. And strangely, that isn't even the strangest part. The strangest part is what one of the most respected physicists alive, Sir Roger Penrose, who shared the 2020 Nobel Prize in Physics for his work on black holes, believes might happen after that. He thinks the ending might be a beginning. Stay with this one, because by the end of time might not mean what you think it means. Why this question refuses to go away. Every civilization that has ever looked at the sky has asked some version of this question. Ancient Norse mythology had Ragnarok, a final battle after which the world burns and sinks into the sea. Hindu cosmology describes cycles of creation and destruction stretching across billions of years, the universe breathing in and out under Brahma. Christian and Islamic traditions speak of a final day of judgment, an ending that reveals ultimate meaning. These stories were built from imagination, not equations. But they were reaching for something real, the intuition that if things have a beginning, they should also have an end. We now know the universe had a beginning. The Big Bang, roughly 13.8 billion years ago, an event confirmed by mountains of evidence, from the cosmic microwave background to the abundance of light elements in the cosmos. If there was a first moment, is there a last one? For most of the 20th century, physicists didn't think much about this question because they didn't need to. Understanding the beginning of the universe was hard enough. But once Einstein's general relativity was combined with the discovery, in 1998, that the universe's expansion is not slowing down but accelerating, cosmologists suddenly had the tools and the motivation to run the clock forward, not centuries forward, not millennia, forward by numbers so large that comparing them to the current age of the universe is like comparing the width of an atom to the width of the observable universe. And what they found waiting out there was not fire and brimstone. It was something quieter and in some ways far stranger. What the ancients never understood about time. To understand how time could possibly end, we first need to understand what time actually is. And here is where the story gets its first real twist, because time doesn't work the way it feels like it works. For most of human history, time was assumed to be universal and absolute. A minute in London was a minute in Beijing, was a minute on the moon, if you could somehow get there. Isaac Newton treated time as a kind of cosmic clock ticking the same way everywhere, for everyone, forever, independent of anything happening in the universe. Then, in 1905 and 1915, Albert Einstein tore that idea apart. Einstein showed that time is not separate from space. The two are woven together into a single fabric called space-time. And critically, that fabric can stretch and bend. Time runs slower near massive objects, and it runs slower the faster you move. Astronauts on the International Space Station age very slightly slower than people on Earth. GPS satellites have to correct for this every single day, or their clocks would drift out of sync with ours within hours. This isn't theoretical, it's engineering. So time is not a fixed, ticking metronome running in the background of the universe. It's a physical thing, shaped by matter and energy, flexible like a rubber sheet under different weights. And if time is a physical thing, shaped by the contents of the universe, then it should change as the universe itself changes. If the universe is expanding, cooling, and eventually emptying out, then time itself might be changing right along with it. This single idea is the seed of everything that follows. The arrow that only points one way. Here's something strange that most people never think to question. The laws of physics, at their most fundamental level, don't actually care which direction time flows. If you filmed two atoms colliding and played the footage backward, the laws of motion wouldn't be violated. The math works the same both ways. And yet everyone knows the difference between a video playing forward and one playing backward. A glass falls and shatters, forward. Shattered pieces leap up and reassemble into a glass, backward, and obviously wrong. Why? If physics doesn't care about direction, why does our experience so clearly have one? The answer is a concept called entropy, essentially a measure of disorder, or more precisely, the number of ways the particles in a system can be arranged while looking the same from the outside. A whole glass has very few arrangements of atoms that make it a glass. A shattered glass has enormous numbers of arrangements that all look like shattered. The second law of thermodynamics states that in any closed system, entropy tends to increase over time. Things move from order to disorder, not because it's forbidden to go the other way, but because it's staggeringly improbable. This is the arrow of time. It doesn't come from the fundamental laws of physics. It comes from probability, played out on an almost incomprehensibly large scale. And it means that the universe, considered as a whole, is sliding, slowly, relentlessly, toward greater and greater disorder. Which raises an unsettling question. What happens when it gets there? What happens when the universe reaches maximum disorder and there's nowhere left to slide? Chapter 1 of the ending. The stars go dark. The first stage of the universe's ending is already underway, and it will unfold over a timescale so long it makes the current age of the universe look like a single tick of a clock. Stars are, in essence, enormous nuclear furnaces fusing hydrogen into helium and releasing the energy that lights up the night sky. But fuel runs out. Our own sun has enough hydrogen to keep burning for roughly another 5 billion years before it swells into a red giant, likely engulfing Mercury and Venus, possibly Earth, before shrinking into a white dwarf, a dense, slowly cooling ember about the size of our planet. Every star does something similar. Massive stars burn fast and die violently, in supernovae that seed the universe with heavier elements. Smaller stars like our sun burn slowly and die quietly, but eventually every star runs out of fuel. Here's the part that's easy to miss. Once existing stars die, new ones become harder and harder to form. Star formation requires clouds of hydrogen gas, and the universe's supply of usable hydrogen is finite. Current estimates suggest that star formation will effectively stop within about 100 trillion years, a number so large that if the current age of the universe were compressed to 1 second, the era of star formation would still be running for more than 2 hours after that second ended. After that, the universe enters what astronomers sometimes call the degenerate era. The lights go out one by one until the last white dwarfs and neutron stars cool into cold dark husks. No new stars, no new light, just drifting embers in an expanding dark. And this is only the first chapter. Chapter 2, the slow death of matter itself. You might think that once the stars go dark, the story is basically over, a cold, dead universe full of burnt-out stellar remnants drifting apart forever. But physics suggests the ending goes deeper than that. Matter itself may not be permanent. Many theories in particle physics, called grand unified theories, predict that protons, the building blocks of all atomic nuclei, are not perfectly stable. They should, in principle, eventually decay into lighter particles, though experiments so far have not directly observed this happening. If proton decay is real, its timescale is staggering. Current experimental limits push the minimum proton lifetime past 10 to the power of 34 years, and some theoretical estimates go much further, to 10 to the power of 39 years or beyond. This part of the story is genuinely speculative. It's a prediction of certain particle physics models, not a confirmed observation, and it's important to be honest about that distinction. If it's true, though, the implications are enormous. Over spans of time that make the age of stars look instantaneous, ordinary matter, the atoms making up planets, dead stars, even your own body if it somehow persisted, would slowly dissolve into subatomic debris, photons, neutrinos, and lighter particles, drifting through an ever emptier universe. Even the densest, most stubborn objects in the universe are not immune to this slow unraveling, which brings us to the objects everyone assumes are eternal, black holes. Chapter 3, even black holes die. Black holes have a reputation as the ultimate one-way doors of the universe, places where matter falls in and nothing, not even light, comes back out. For a long time, physicists assumed that once formed, a black hole would exist forever, a permanent scar on spacetime. Then, in 1974, Stephen Hawking showed that black holes are not eternal after all. Using quantum theory near the event horizon, Hawking demonstrated that black holes should slowly emit radiation, now called Hawking radiation, and over immense timescales, lose mass and eventually evaporate entirely. It's a genuinely strange result. Pairs of virtual particles constantly pop in and out of existence everywhere in the vacuum of space, and near a black hole's event horizon, one particle of the pair can fall in while the other escapes, carrying away a tiny sliver of the black hole's mass and energy. Do this often enough, over long enough timescales, and the black hole shrinks away to nothing. This isn't a fast process. A black hole with the mass of our sun would take on the order of 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, millions or billions of times the mass of the sun, could take on the order of 10 to the power of 100 years or more. But extremely slow is not the same as never. Given enough time, and in this story we have essentially unlimited time, even black holes complete their evaporation, releasing their remaining energy in a final burst before disappearing from the universe entirely. Once the last black hole evaporates, something remarkable has happened. Every large complex structure the universe has ever produced, stars, planets, black holes, galaxies, is gone. Chapter 4. Heat Death, the quietest possible universe. What's left after the stars die, matter decays, and black holes evaporate is a universe unlike anything we can easily picture. An almost perfectly uniform bath of extremely low-energy radiation, spread across a volume of space so vast that the distance between individual particles dwarfs the size of galaxies today. No stars, no structure, no meaningful temperature differences anywhere for energy to flow between. This is the scenario physicists call heat death, or more technically, the state of maximum entropy. Remember the second law of thermodynamics? The tendency toward disorder? Heat death is what happens when that process finally, fully completes. There's no more order left to lose. No temperature differences to drive change. No engines left to run, because an engine requires a hot side and a cold side, and in this universe, everything is the same temperature, essentially and forever cold. This is where our story gets philosophically strange, because remember what we said earlier, the arrow of time is powered by entropy increasing. If entropy has nowhere left to increase, if the universe has reached its maximum possible disorder and just stays there, does time still mean anything at all? Some physicists argue that in a state of true heat death, time effectively loses its meaning. Without change, without processes, without any way to distinguish before from after, the concept of time may become, in a very real, physical sense, undefined, not stopped exactly, just no longer applicable, the way asking what's north of the North Pole stops making sense once you're standing on it. This idea that time might not simply run out, but rather stop meaning anything at all, is one of the most genuinely mind-bending ideas in modern cosmology. It's not that the clock stops ticking, it's that there may no longer be a clock for the concept to apply to. But is heat death really where the story ends? 3 rival endings. Here's where honest science requires us to admit something. Heat death, while currently the leading hypothesis, is not the only serious candidate for the universe's fate. Cosmologists have proposed at least 3 competing scenarios, and which one is correct depends on details we haven't fully pinned down yet, particularly the exact behavior of dark energy, the mysterious force driving the universe's accelerating expansion. The Big Freeze, which is essentially heat death described above, assumes dark energy continues to push space apart at a steady or slowly changing rate, expansion continues forever, and the universe simply thins out into cold nothingness. This is currently the scenario best supported by observational data, based on measurements of the expansion rate from surveys of distant supernovae and the cosmic microwave background. The big crunch is the opposite. If dark energy weakened over time, or if gravity ultimately won out, the universe's expansion could slow, stop, and reverse. Galaxies would begin rushing back toward each other, temperatures would rise, and the universe would collapse back into a state resembling the Big Bang in reverse, an unimaginably hot, dense point. Current observations make this scenario look unlikely, but it hasn't been completely ruled out. The Big Rip is more violent still. If dark energy is not just constant but actually strengthening over time, a possibility some theoretical models allow, though current data doesn't clearly support it, the expansion of space could eventually accelerate so dramatically that it would overpower every other force in nature. First, galaxies would be torn apart, then solar systems, then planets, then atoms themselves, in a runaway process ending in a finite time rather than stretching out to infinity like heat death does. There is also a fourth, more unsettling possibility called vacuum decay. Quantum field theory suggests that the vacuum of space, what we think of as empty, might not be in its lowest energy, most stable state. If that's true, a small bubble of truly stable vacuum could, in principle, form somewhere in the universe, possibly through random quantum fluctuation, and expand outward at close to the speed of light, rewriting the laws of physics as it goes and destroying anything in its path without any warning at all, because it would be moving as fast as the information that could warn you. It's important to stress, this is a mathematically consistent possibility under current theories, not something with observational evidence behind it. Current measurements of the Higgs boson's mass from experiments at CERN's Large Hadron Collider keep this scenario on the table as a live theoretical possibility, sitting right at the edge between stability and instability, but on the table as possible is very different from expected or imminent. If it can happen at all, current estimates suggest the timescales involved would vastly exceed the current age of the universe. 4 different endings, each mathematically consistent with the laws of physics as we understand them. each requiring different assumptions about the ultimate nature of dark energy, a substance that, remarkably, we still don't understand at a fundamental level, despite it making up roughly 68% of the total energy content of the universe. This is honest science, multiple viable answers, and an admission that we don't yet know for certain which one is real, the Boltzmann brain problem. Before we move to Penrose's radical proposal, there's one more strange idea worth pausing on, because it emerges directly from heat death, and it's genuinely unsettling. In an infinite universe that has reached maximum entropy and simply persists, with quantum fluctuations still occurring, even if extraordinarily rarely, statistically, almost anything that's possible will eventually happen, given enough time purely by random chance. This includes, in principle, the spontaneous random assembly of a fully formed conscious brain, complete with false memories of an entire life never actually lived, a so-called Boltzmann brain, named after the physicist Ludwig Boltzmann, who pioneered the statistical understanding of entropy. This isn't a fringe idea invented for shock value. It emerges directly from the mathematics of an eternal heat-death universe, and serious cosmologists have written about it as a genuine puzzle for cosmological models, sometimes even using it as a tool to argue that certain models of eternal inflation must be wrong, since those models would predict that random Boltzmann brains vastly outnumber ordinary observers like us, which contradicts what we actually observe. To be clear, this remains a statistical thought experiment and a theoretical constraint on cosmological models, not a claim that such brains have ever actually formed, but it illustrates just how strange the mathematics of eternity can get. Roger Penrose's radical answer. Now we arrive at the heart of this story, an idea proposed by a man who has spent much of his career staring directly at the strangest corners of physics, Sir Roger Penrose. Penrose is not a fringe figure. He is one of the most respected mathematical physicists alive, co-developer with Stephen Hawking of the singularity theorems that showed black holes must form under very general conditions in general relativity, and a recipient of the 2020 Nobel Prize in Physics for this work. When Penrose proposes something unconventional, the physics community listens carefully, even when they disagree. His proposal is called Conformal Cyclic Cosmology, or CCC, and it starts from a beautifully strange observation. In the far future, the heat-death universe we just described, filled only with extremely low-energy photons stretched out across near-infinite space, there is no matter with mass left. Only massless particles like photons remain. And here's the key mathematical fact Penrose leverages. Massless particles don't experience time or distance scales the way particles with mass do. In fact, for a universe containing only massless radiation, the equations of general relativity can be mathematically rescaled, a technique called conformal transformation, so that the infinitely large, infinitely old heat-death future becomes indistinguishable mathematically from an infinitely small, infinitely hot Big Bang-like beginning. In plain language, Penrose's mathematics suggests that the endlessly stretched out, cold, empty future of one universe could be mathematically identical to the unimaginably hot, dense beginning of the next one. The ending folds seamlessly into a new beginning. Not through a physical collapse, like the Big Crunch, but through a geometric identification. The two states are, in Penrose's model, actually the same state, viewed at different scales. Under CCC, our universe is not the first, and it will not be the last. It's one aeon in an endless sequence, each one ending in what looks like heat death, and each ending seamlessly becoming the beginning of the next. Penrose has even suggested a possible way to test this idea, looking for circular patterns in the cosmic microwave background, the afterglow of the Big Bang, that might represent the imprint of gravitational wave events like supermassive black hole collisions from the aeon before ours. In 2010, Penrose and physicist Vahe Gurzadian published a paper claiming to find such circular patterns. It's important to be direct about what happened next. This claim faced substantial criticism. Multiple independent teams reanalyzed the same cosmic microwave background data and concluded that the patterns were statistically consistent with what you'd expect from random noise in a standard non-cyclic universe, not evidence of a genuine signal. Penrose and his collaborators have disputed some of these rebuttals, and the debate has continued in the scientific literature. As of now, conformal cyclic cosmology remains a minority position, respected as a serious and mathematically rigorous idea, but not supported by the mainstream consensus of cosmological evidence. This is exactly the kind of situation where scientific honesty matters most, a brilliant, legitimate hypothesis proposed by a towering figure in physics that has not yet and may never pass the test of observational confirmation. What would it mean if Penrose is right? If CCC is correct, then the entire distinction between the end of time and the beginning of time collapses. There would be no true ending at all, just an endless sequence of aeons, each one blind to the ones before it, each one believing, as we do now, that it emerged from nothing and will fade into nothing. It would mean that heat death, the coldest, emptiest, most meaningless seeming state physics can imagine, is secretly the most important moment in the entire history of existence, the hidden seed of a new universe. It would mean asking, what happens after time ends, is a bit like asking what's north of the North Pole. The question assumes a boundary that, geometrically, might not actually be there. the honest uncertainty at the center of this story. Let's be completely clear about where the science actually stands, because this is a story where the temptation to overstate certainty is enormous, and resisting that temptation is what makes the story worth trusting. What's well established? The universe is expanding, and that expansion is accelerating based on multiple independent lines of evidence. Stars will exhaust their fuel and die. The second law of thermodynamics reliably predicts increasing entropy in closed systems. Hawking radiation is a mathematically robust prediction of quantum field theory applied to black holes, even though it has not yet been directly observed, since it's far too faint to detect from real astrophysical black holes with current instruments. What's genuinely uncertain? The long-term behavior of dark energy, which determines whether we get heat death, a big rip, or something else. Whether protons decay at all, whether vacuum decay is a live physical possibility or purely a mathematical curiosity of the equations, and whether Penrose's conformal cyclic cosmology describes something real or is an elegant piece of mathematics that nature simply doesn't use. This is what real science looks like at its outer edges, not a wall of certainty, but a frontier of competing, rigorously argued possibilities, narrowed down slowly, carefully by evidence over generations. Why this question matters to you right now? It's tempting to hear all of this and think, none of this matters. These timescales are so vast, 10 to the power of 100 years, numbers with more zeros than there are atoms in the observable universe, that they have nothing to do with a human life measured in decades. But that misses something important. This question forces us to confront what time actually is, at the deepest level we currently understand it. It reveals that the flow of time we experience every single day, the reason memories feel different from anticipation, the reason we can act but not unact, the reason grief and hope both make sense, is tied to a cosmic process of increasing disorder that will not run forever in its current form. Time, in some sense, is a temporary feature of a universe passing through a particular phase of its existence, not a fixed backdrop that was always there and always will be. And if Penrose is right, even that temporary feature might be part of something recurring, a rhythm playing out on a scale so vast that our entire observable universe, from the Big Bang to the last evaporating black hole, is just one note in a song, with no first note and no last one. We began this video asking a simple question: does time end? The honest answer science can currently offer is layered. In the form we experience it, change, causality, the difference between past and future, time very likely does fade into meaninglessness in the far future, as the universe approaches maximum entropy. But whether that fading is a true ending, or simply an invisible seam connecting one chapter of existence to the next, may be one of the deepest open questions in all of physics. Somewhere out there, unfathomably far in the future, the last black hole will finish evaporating. The last flicker of usable energy will fade into the same uniform temperature as everything else. And in that silence, if Penrose is right, the conditions for an entirely new universe may already quietly be forming. The deeper we look into the universe, the more it begins to look back at us.